This just leaves a root pi here. Because you got like pi to the first power over pi to the 1/2. You subtract the exponents. This just becomes root pi. What am I trying to solve for? This right here. So let me just write down where I am right now. I have 1/5 equals 2 root 5 pi dr dt. What did I do there? Just put the 2 out front. I put root pi and root 5 together under one root. And now my dr dt. And now I'm just going to divide that on both sides. So just divide that over, and that should be our result. So dr dt should be equal to 1 over 10 root 5 pi. Okay, that's what I get when I bring this over here. And then I need the units. So how do we get the units for this answer? Radius in this problem is measured in feet, and t is measured in seconds. So this is going to be feet per second. Now, you could go on your calculator and get a decimal for that, but that's the exact answer.
You'd be okay with that?
I would be very okay with that. Yeah, I would prefer to see it this way because any answer that you get on your calculator is going to be an approximation.
Yes.
Yeah. Are y'all still okay with this? We're just beginning. These are easy equations to work with, and the geometry is easy. Yes? Okay. How to get what? When I divide both sides here by 2 root 5 pi, and I divide this side, I basically get 2 root 5 pi, and the 2 and the 5 become a 10.
I was just thinking all this talk about circles and whatnot made me think of what's a pirate's favorite formula?
A pirate's favorite formula. I don't know.
Pi r squared?
Is it a coincidence that the derivative of the area is this formula for the circumference?
2 pi, well, it's not though because of the dr dt. So it is more of a coincidence, but the dr dt there really makes it very different than circumference. All right, so now let's go into 3 dimensions. Let's look at something other than a circle. So how about a sphere? We have a sphere. It's expanding at a constant, the radius is increasing at a constant rate. This number is going up at a constant rate. And look at the volume of this thing. 100, right? 200, 300, 400, 500, 600, 700. Does it seem faster or no? Yeah? Okay. So the sphere is growing. The radius is growing at a constant rate. We're going to be interested in knowing how fast the volume is changing. Not the area, volume. Here it is. If the radius of a sphere is increasing at a constant rate of 2 feet per second, then how fast is the volume increasing when the volume is 36 pi cubic feet? So this is like blowing into like a balloon, you know, at a constant, you're putting air into a balloon at a constant rate. Or sorry, no, I take that back. No, let's scratch that. That'll be the next example. Because that's different, because if you're filling up a balloon with constant amount of air going in, then the volume's changing at a constant rate. Here, the radius is, so just scrap that, never mind. All right, well, pictures. general, instant, given, want, equation. All right? My general picture is a sphere, right? It's my general picture is a sphere. If you have never gotten comfortable drawing spheres, just draw a circle, and then about midway through, draw like this ellipse kind of thing like that. So there's your sphere. And you put a dot here in the center like that. There's your sphere. That sphere is growing, right? So I'm not going to fix anything on that. I'm just going to leave it as a sphere. I'm going to draw another sphere over here. This is the one, the instant in time. Is there anything you can tell me about the instant in time? The volume is what? 36 pi cubic feet. So here for this one, the volume is 36 pi cubic feet. Anything else? Jace, you're up. What can I fill out here? Anything else? Any other information?
Given the constant rate of 2 feet per second.
Okay, so what is that 2 feet per second? It's a rate of change of what?
The radius of a sphere increasing at a constant rate. So as the sphere expands,
Yes.
it expands at a constant rate.
You're given something though. This right here is a derivative. What is it? It's d something, d something.
dA over dt.
Is that your change in area? Read it. The radius is increasing, right?
Yeah.
That's your change in radius.
Yeah.
So dr with respect to t, because of time, is 2 feet per second. Razul? Do you know what we want? I'm going to help you out. It's d something dt is what we are interested in. What though? Just read the bottom line here. How fast is the what? A? Read it. How fast is the volume? Right? Volume. Not area, the volume. So they want to know how fast the volume of this thing is increasing at a certain point in time. So not dA, dV. Now, we also need to know when we want this. When are we going to snap the picture? When are we going to hit the pause button? Hold on. Brian, when are we hitting the pause button?
At 36.
At what's 36? Yes. When what is, though? The volume. Okay, so see when I write when volume is 36 pi cubic feet. You just got to be sure you know what it is that you know. Don't put like radius because it's not the radius, right? All right. We're cranking. Tatum, you're up. Tatum, I need an equation. I need an equation that relates the radius of a sphere to the volume of a sphere. And I don't expect for you to know that off the top of your head, but you're looking at something. You have your formula sheet there? Good. Okay, so what do you got there, Tatum? Cubed. Okay, this is a formula on your formula sheet. It has a picture of a sphere there, doesn't it? And it tells you that the volume of that sphere is 4/3 pi r cubed. There's our equation. What's great about this equation, it has v in it, so when I differentiate with respect to time, I'm going to get a dv dt, which is what I'm looking for. And I'm also have an r in here, which means I'm going to get a dr dt, and that's something I'm given, right? All right. Let's go ahead and do the differentiation. So here comes my derivative time. It's derivative time. And let's see here. Trey, you're up. Got to differentiate this with respect to time. So Trey, you want to do the left side? dv dt. You did that so easily, I think you want to do the right side also. Right?
There's two constants, they both carry.
Yep. So just ignore those, right? That's all you have to do. I'll write them down, but you just ignore them. So Trey, all you have to do is tell me what the derivative of r cubed is with respect to time. Okay. Good. You're there. Come on. dr dt. There you go. That's it. So 3r squared. That's your power rule. But then chain rule says go inside, take derivative of the r after you're done, and you get dr dt. And now we take a look at that. We're done with the differentiation, right? That was it. There's no product rule or anything there. We just do a quick check. Are we happy to see dv dt? Absolutely. 4/3 pi 3. Crap. R. I don't know R, do I? I don't know R. I know what V is at the moment I snap the picture, but I don't know what R is. But I can get R. What about dr dt? Yeah, I'm happy to see that because I have a 2. So the only thing I have left to do right now is go figure out what R is. So if I go back to that picture I had, where I had the instant in time, and I had volume was 36 pi cubic feet, right? If that's my volume, then I can come down to my volume formula. 36 pi must be equal to 4/3 pi r cubed. Right, so volume was given to me, must be equal to the formula for volume, and I can solve for r. So what should I do here to solve? Cancel the pi's, divide by pi on both sides. How about divide by 4? If I divide by 4, what do I get? Divide that by 4? 9? And then multiply both sides by 3. Right? 27 is r cubed. So what's r? 3. The cube root of 27 is 3. So your radius is 3. So now I know that, and now I can go figure out everything out. Do y'all see that this part right here, this part I just did right here, was what we started with in the very beginning? Where I said you have to be able to do these in order to do these problems, because at the very end of these problems you have to be able to maybe go back and solve for one of the variables. All right, dv dt, the instantaneous rate and change of volume with respect to time for this sphere is 4/3 pi times 3 times, what was r? 3 again? Squared times dr dt, which is 2. So this is just plugging everything in. R goes in here, dr dt is 2, and that's just a number. Those 3's are gone. What is that? Come on, arithmetic, let's do it. 9, 30, 72 pi? 72 pi. 72 pi. Heidi? 72 pi what? Feet cubed, because it's a volume, right? So feet cubed, and then that it? Feet cubed? Per second. And that's because your rate is always going to be over something with time, right? You won't admit it, but this is fun. You won't admit it. You ready for something else? This is a classic problem. Take a moment to read it. We are, for the sake of this problem, we are assuming that the Earth is flat, which it is, by the way.
Did you ever see that argument of Neil deGrasse Tyson?
His argument for a flat Earth?
Yeah.
I have not seen him say that.
So, no,
Not-
he's not arguing for it. No, there was a rapper, Bob. He was a guy that sang like a song, Airplanes in the Night Sky. Anyway, point is, he's some shitty rapper. He made a comment saying the Earth is flat, and then he called out Neil deGrasse Tyson saying some shit to Neil deGrasse Tyson. And then Neil deGrasse Tyson put out his own
Reply.
So what? Yeah,
His
own
reply. I'll look it up. All right. Everyone got it? No? Still writing? Oh, you don't need to copy it down. I'll move it up a little bit here. I'm actually going to make it a little bit smaller because I need some room to work here. It's picture time. I love drawing pictures. General. I'm going to give myself a little more room. Instant. All right. My general picture, I have a plane flying horizontally 2 miles high at a speed of 600 miles per hour. The plane is headed directly over a ground-based radar station. At the moment the plane is 6 miles from the radar station, how fast is the distance between them changing? All right, so here we go. That's the ground. This is my radar station. It's impressive. I've been doing this for a long time. Okay, so don't be jealous. I draw radar stations every semester. I've gotten good at it, as you can see. We are actually going to think of the radar station as a single point on the ground. Okay, we're not going to take into account how high off the ground it is. We're just going to consider it to be a point. There's my radar station. And now, a plane. And this is where you'll probably get really jealous, okay? Because this is going to blow you away. Look at that. Can you tell what that is? What kind of plane that is? Yeah, I know. Check that out.
Did you ever think of applying for Blue's Clues?
Yeah. For what? Blue's Clues? Is that what you said? There we go. All right, so we got our plane. Now, this plane is moving overhead like this, right? The plane is moving overhead. That's it. I mean, that's pretty much all I can draw in my general picture right now. That's all I really care to draw. Because everything's in motion, right? Now, the instant in time, I can draw a little more detail. Whatever. Oops, I don't know what happened to it. There's my plane. It's morphed into something else. Okay, at the instant in time, what can I actually label? So you see where it says at the moment the plane is 6 miles from the radar station? At the moment the plane is 6 miles from the radar station. Right? That means straight line distance. Straight line distance. 6 miles. Not ground straight up to plane. This means straight line distance from the radar station to the plane is 6 miles. That's fixed, right? In my instant picture? Anything else that's fixed in that picture? The altitude, right? Which is distance from the plane down, straight down, is what? 2 miles. Well, you know what? Now that we've drawn that, isn't that also here? Isn't this 2 no matter where the plane is? So I can fix that in this picture. I can't tell you where it is. Horizontally I can't, but I can tell you vertically it's 2 the whole time, right? Further, if I start to look at that picture and this picture and start to look at similarities, I know that there is a distance from here to here, except here it's changing and there it's not. So I'm going to call this H for hypotenuse. Is that all right? Can you see the right triangle coming to life here? That's a hypotenuse. I should have put what I've given and what I want. And then the equation. Luis, sorry. Anything here? I'll help you a little bit. Speed? What speed? What are you talking about? Oh, the 600 miles per hour? Wait on that. That's harder to get. Can you tell me what you want? Look at your picture. How fast? How fast is the distance between them changing? So in your picture, what represents the distance between them? The hypotenuse. You want to know how fast that's changing, right? So you want d h dt. That's what you want, right? When do you want that? At the moment when h is 6 miles, right? I want to know how fast that h is changing, right? Back in this picture, how fast is this h changing at exactly the moment that it's 6? Y'all okay on that? Following this? You don't get it? Okay, so it's like you're measuring from here to here, right? As this plane flies over, this h is starting to get shorter and shorter. Until it gets overhead, then it's 2. Then as it goes past you, it's going to get longer and longer. So as the plane flies, h is always changing. So you would like to know, at the moment the plane is 6 miles from the radar station, how fast the distance between them is changing. So you want to know how fast h is changing with respect to time. Does that clarify it a little bit? Okay. But you want to know it exactly at this moment. This is the hardest part right here, I think. The given part. You know it's the 600, right? Because 600 miles per hour is a speed, isn't it? It is a rate of change. So I'm going to put it here. Something is 600, I'm going to even write it this way, miles per hour, like that. This is a derivative, but it's the derivative of what? D what? D what? A, dA.
Because I'm thinking the equation is going to be...
I don't see A. Where's A?
A squared plus B squared equals H squared.
Okay, so you want to label this A?
Yeah.
Okay, so I know where you're going, but I'm trying to make everyone kind of, okay? Like, I'm not trying to like insult you. But look, what you just did was introduced a new variable. That's what we have to do right now. We have to introduce a new variable, and that is, think about it this way. This plane, right, as it's flying this direction, right, think about it as a point. As it's flying that direction, that point is moving at 300 miles per hour, isn't it? Isn't that the same as saying that this point down here on my triangle is moving 300 miles per hour this way? Right? 600, sorry, 600. My fault. So if I call this side of this triangle, you wanted to use A?
Or whatever you want to use.
Let's use A. Okay. Capital or lowercase?
I like lowercase.
Lowercase? Okay. Lowercase a. Then A here is the distance from here to here, isn't it? That's that distance. And A is changing. How fast is A changing? 600 miles per hour. So that 600 is dA dt. But you had to introduce that new variable. You have to come up with that yourself. All right, 2 miles is fixed. As the plane moves, that doesn't change. But as the plane moves, h changes. As the plane moves, a changes. Yes? There's one thing not right here, though. Is a growing or shrinking in this picture? It is shrinking, isn't it? And because a is shrinking, this rate of change needs to be negative. Okay? Because a is shrinking in the picture. Now, if you mess that up, your answer will be incorrect. So you have to pay attention to what's going on. So your picture should somehow indicate that. A, as the plane flies over, will be shrinking. Got it? All right. Is that enough? Do we have enough to try and come up with an equation? I think so. Can you relate using anything you know? Dig deep into the cracks of your short-term and long-term memory and try and find an equation that would relate a to h, and you're looking at this picture. Pythagorean identity. A squared plus b squared equals c squared. It's a squared plus 2 squared equals h squared. That is an equation that relates the three sides of the triangle. So my equation is a squared plus 2 squared equals h squared. And see, when I differentiate this, I'm going to get a dA dt in here because I've got an a. And I'm going to get a dH dt in here because I've got an h, and that's what I'm looking for. Any questions? Differentiation time. What is the derivative of this thing? Karen? Where's Karen? Karen, right? Okay. What's the derivative of this right here with respect to time? So what's the derivative of a squared? 2a. Is that all, though? You've taken care of the squared. So what's the derivative of a now with respect to t? dA over dt. All right, Sophia?
Yes.
What's up next? We just did the derivative of a squared, right? Plus 0, right? So it won't be there. Equals. So we need the equals here. 2h. Yep, times dH over dt. That's it. There it is. There's an equation that relates it all together. And now we just double check. Do we have everything we need? Do we know A in the problem? At this instant in time, do we know A? Not directly, we don't, right? So I don't quite know what that is. How about dA dt? Yeah, that's negative 600. How about h? Do we know h at the moment in time? Yes, it's going to be 6. How about dH dt? That's what we're looking for, so I'm happy to see it. So there's only one thing I don't know, and that's A. So now I come back to this picture. Now I can be at the instant in time, come back to this picture, and I just say, hey, look, this is A, right? I have two sides of a right triangle. I can get the third one easily, right? This is just going to be a squared plus 4 equals 36. So a squared equals 32. So a is root 32. So I just do some algebra there to solve for a. And now I have everything I need. I'm going to kill the 2's just because they're just in the way. So now I put a, which is root 32, dA dt, negative 600, equals h, 6, and then dH dt, which is just dH dt. And I'm trying to solve for dH dt, so I just divide both sides by 6. And if I do that, I get negative 100 root 32 equals dH dt. Was that a question? Yes.
What happened to the twos?
I just divided both sides by 2. I just didn't, they're just there. I mean, I could have kept them, but they're going to go away eventually.
Professor,
Yes?
how come the 6 is not negative like the h if that distance is going to be shrinking as well?
Because h is a distance. It's not the rate at which it's changing. It's like if I froze that plane in time, measured the distance, it would be a positive number.
It's frozen.
Yep. Yeah. All right. Somebody on their calculator real quick, tell me what that is. We'll get a decimal approximation. So dH dt is approximately
Negative 565.
565.68. All right, what are my units here? What are the units of this answer? H, right? H is the distance, right, from here to here? That's measured in what unit? Miles. And then per, the time in the problem is measured in hours. So basically that plane is straight line distance approaching. It's almost like if you were reeling that plane in, okay, with a fishing rod down here, you'd be reeling it in and the string would be coming in at 565 miles per hour. The plane's going 600 miles per hour, but the rate it's closing towards you is 565. All right, let's look at one more. We won't be able to do the whole thing. Oh, that's the animation. We don't need it. Yeah. Look at this problem here. A plane is flying horizontally 200. Oh, wait a minute, same problem. No, not quite. Look at what it's asking for at the very end. At the moment the plane is 6 miles from the radar station, how fast is the angle of the tracking radar changing? So now what we're doing is we're saying, okay, we've got the general picture. We've got the ground. We've got the radar station. We've got the plane, right? We know that this is 2 miles, but we want to know not the distance between these anymore. We want to know the rate at which the angle is changing, as we track the plane overhead. So if we connect from here to here and call this theta, that's what we're interested in, that theta, right? Now the instant in time, we have the ground, radar, plane, 2. Here we have 6. Right? Did y'all see the pictures there? How this is different than the last one? We're interested in this angle as opposed to this distance. But they tell us about this distance, right? At the moment the plane is 6 miles from the radar. So this information is the same from the last problem. What are we given? What do we want? And what's our equation? I think we can get that before the class ends. All right. Well, we're given the speed of the plane still, right? So we still have to come over here and label this A. Because that A is changing, right? So that's still the same. dA dt is what? Negative 600, right? Negative 600 miles per hour. But what is it that we want? The rate at which the angle is changing. d theta dt is what we want. How fast does the angle change with respect to time? And when do we want that? When what's equal to 6? When, yeah, we haven't labeled that, have we? So we better label it. So we want to know how fast the angle's changing when that's 6, but we never labeled it over here, so let's call this h, and we'll just say over here when h is 6. So this is the same as the last problem. This is the same as the last problem. This is different, right? Which means our equation is going to have to be different. Let's see here. Who's the lucky one? Who's the lucky one here? It's going to be Frank or Marissa. I'm getting two brains on this one. I need an equation. Frank or Melissa, or Marissa, sorry. That relates what two variables? Frank or Marissa?
Theta and time.
Theta, I agree with theta. We need to link somehow theta to what? A.
So is it using a like sine, cosine, tan?
Any equation you can think of that relates A and theta together. And you want to be working off your general picture here.
So you have to, couldn't we just use sine?
Sine of, are you saying sine of? So look at this right triangle. Sine is opposite over hypotenuse, right?
Yeah.
So sine would be this over that. That's not quite what you want.
That'd be cosine.
Cosine would be this over this, right? Sorry, you said cosine?
Yeah.
Cosine would be adjacent over hypotenuse? Could he use that, everyone? Let's look at it real quick. I don't have a lot of time. Don't write this down. It's not going to work, but let's take a look at it.
Fair enough.
Okay, let's see why not, okay? Here's an equation, right? You have theta and A in here, and that's what I told you needed. Frank, if I differentiate this, do you agree I'm going to get a d theta dt somewhere? Because I've got a theta in here. When I differentiate with respect to time, I'm going to get a d theta dt. Okay, great. D theta dt is what I want. I'm going to get a dA dt also, because A's in here. But what else am I going to get? dH dt, and I know nothing about dH dt, do I? So that trig function, although it works, you don't know anything about h. But you do know that this one's always 2. So can you use these sides instead? Tangent. There you go. Tangent theta will work. So look, everyone, our equation is going to be tangent theta equals what? What is tangent of theta according to that triangle? 2 over A. 2 over A. Now, I'm supposed to differentiate this with respect to time right now, aren't I? I'm going to do something real quick before I do it, though. I'm just going to multiply both sides by A. That's just some algebra, right? Multiply both sides by A. I'm only going to have time for the derivative. Alberto.
Yes.
Okay. I need the derivative of this with respect to time.
Okay, so that A is going to come down since it's flat.
What's that?
The A is going to be 1.
You're differentiating with respect to time.
dA dt.
Okay?
And then it's going to be
What is this right here?
product rule.
It's product rule, right? Okay. Because you have a product here, when you differentiate this, you have to use a product rule. Now, I could have left the A over here, but I'm a little scared on how people are going to differentiate that. So I just brought the A over. Product rule. Try it again. So derivative of the first one, which would be d A d t times tangent theta. All right. Plus, all right, I know we have 1 minute left, but this derivative right here is the one that gets everyone. Okay, what's the derivative of tangent theta? Secant squared theta, right? Secant squared theta. But then chain rule says take the derivative of what's in there. And what is the derivative of theta with respect to time? D theta dt. So this is times d theta dt. That part right there is the part that most people miss. Okay, it's chain rule. You're doing derivative of tangent of something is secant squared of that something. Then you go inside, take derivative of theta with respect to t is d theta dt. But you're not done. Times a. And then that's your product rule, right? That's your product rule done? Equals derivative of the right side. 0. All right, we are out of time. Yeah, that we'll just pick up with that. I would say, start your homework, see how it is. .7, it is what it is. I'm just the messenger. They're fun problems. You'll enjoy the homework.